Dan's walking his dog. He's going to show us the forest across the street.
So
And we were just chatting about agoric. So because RChain turned something off with smart contracts, Dan had been investigating agoric, which is they're all about smart contracts on various platforms. So and agoric is partnering with Substrate, and that's the Substrate from Parity, and that's the project that Joshi is involved with. So it's that's the beauty of Colab, is being exposed to these other platforms.
So this is Island Park across the street here.
Oh, look at that.
So we'll be walking through the park.
Cool.
This is there's like a sister city, and so that sculpture there is clouds or something. It says oh, Taiwan.
Oh, look at that.
Island, Taiwan.
Oh, okay.
And here's where the little kids play. Mojo likes to play with them.
That's so nice to have a park within walking distance of your house.
It's really excellent. Ooh.
Yeah, that's wonderful.
Oh, it's not quite dry enough to go on the slide. I'm just thinking about it. So I didn't know that they were using Substrate, actually, so that's cool.
Yes, right. So you know, there's our RChain world, but with Joshi's involvement with Substrate and Parity and Polkadot, and then agoric is that missing piece, that component for the smart contracts, and they're using a subversion of JavaScript, which is Jessie, because of the higher level of security and something that you mentioned, object capabilities. So with the object capabilities adds that additional level of security and structure to the smart contract. So
preach, brother, man! Listen to him go.
So
well, I'm impressed.
So all these things I've been kind of hearing about on our Colab meetups is kind of representing itself in with this agoric. So yeah, it was exciting to sit and listen to the video.
Yeah, those are the guys that invented object capabilities.
Oh, well, I mean, this is it keeps getting better and better.
Right.
You know, so when I think of blockchain and the world of smart contracts, it's all about, you know, flexibility and, you know, getting this widespread adoption. So, you know, having a Substrate, which is, as I watched, you know, a video on that, you know, Substrate yesterday, today, and tomorrow, and starting to get an understanding of what their project is. And it's essentially, it's a framework. So it's a framework that gives you this tremendous flexibility on building your own sort of personalized blockchain. But they with their teams, they want to be able to leverage existing blockchains that are out there.
Two have met, haven't they?
I have no idea. Okay. I don't recall.
Okay.
So
could you tell me what was turned off in rholang? I probably won't understand it, but
okay. So
what a great day after such a mess last night.
Let's see here. So
we're getting a little too spunky here.
So, Jim, you remember Dan had that question on consensus with Greg at Monday morning. He was, um, if Dan can hear us, maybe he might be able to. Dan, what
I'm
is
here.
what is turned off within RChain that stops you from working on the smart contracts with the R node?
Well, hey, do me a favor. So you found Agoric via a link I dropped in, right?
Just the
Maybe you
name.
didn't.
Yeah, it would. You
Oh,
you
okay.
just mentioned Agoric, and then I just Googled it.
So I dropped a link in a couple channels. One's the pub RChain development, and one is the collab governance thing.
Okay.
Jim, do you recognize that link I dropped? I think you saw it.
Yeah, I can. It was pointing to some JavaScript code.
Right, but the JavaScript code was a comment about the issue that he's asking me about.
Gary, it's actually ticket 3260. So
Yeah,
if you pull up,
I'm looking at it now.
yeah, so 3260 has with the comments that you can get better understanding of what it is that they turned off. So I think it's you can pass Rev to a wallet, but so it's what feature will be available at Mercury. So you'll be able to pass Rev to a wallet, but once in that wallet, being able to utilize that Rev to execute on a smart contract is going to be after Mercury. So it's
Well, I don't know when they're working on this issue now, as far as I know.
okay.
They've actually, I think that their work they've given it a different number, but that's linked. I think there's a comment from Chris Boscolo.
Yeah, and I haven't been into the ticket for a few days, so there may be some updates. So
Okay. Anyway, I think they are. There's some questions from Artur that make it clear that his head is deeply into this and stuff.
oh, okay, all right.
Unfortunately, I think he asked me what a confused deputy is, which means that he doesn't know object capabilities.
So the word you said was a confused deputy.
That's correct.
Okay, that's a new term for me as well.
Yeah. So, have you heard of clickjacking in the web?
No, I have not.
Oh, interesting. Okay. Clickjacking is the most. It's sort of the most manifest version of the confused deputy problem in the world today. You know, normal people like lose their identities and cut stuff because of it.
Okay. Interesting. I like.
So now here we come to a question of civil disobedience or something here. So this thing says that the powers that be don't think it's safe for me to walk the woods because there was too much rain.
Okay.
I'm going to go a little bit anyway.
Okay. Well, I like the format of the office hours this morning. It's Out Walking with Dan should be the title. And you know, just you know, these types of conversations about new concepts and new you know, resources that are out there. So we're talking about Agoric, which, you know, is a new concept, and I wasn't aware that they were the ones that created object capabilities. And clickjacking, learning about that. So you know, a big piece of all this is, you know, these terms and terminology and
Right.
what they are and how that all fits together. So this is a great use of office hours.
Is this a time when we might have a in-service on object capabilities and confused deputies, or are people just coming up to speed? Holder, you know, catch as catch can.
No, we absolutely, you know, I've got nothing better to do. I'm in the RChain project because I want more people to use object capabilities. Okay, here we've come to an impasse. There's a whole bunch of mud there, so we're doing a 180. But you get an idea,
Right.
So I don't have to pay taxes for this because I live in the next town over. But this is maintained, you know. Somebody carefully mows the stuff for 1 feet out on each side and all that kind of stuff.
Oh wow.
And it was this morning. It's not up to their standards, so they said don't go there.
Yeah. Yeah.
But yeah, okay. So let's see. Confused deputy is a good thing to know. But I mean, it's kind of, if you guys were living in the world of cross-site request forgery and clickjacking, you know, you would have all this pain, and I would tell you that I could you know, ease your pain. But since you don't live through that pain, I don't think that that's particularly the thing we should do. If you're looking at all those links to the JavaScript in the RChain ticket, I think one of the last links is a YouTube video.
Okay.
It's to Mark Miller at San Francisco Blockchain Week.
Okay.
And that talk is so excellent. He tells like the whole 30 years of research and all this kind of stuff in about an hour.
Ah, okay.
And if you want, you can click. The part that I've bookmarked is like an hour and 20 minutes into the talk, where he talks about kind of the most interesting, you know, the top level where you actually get to do the really, really cool stuff.
Okay.
On the other hand, maybe like the middle third of the talk or something like that is where he takes really basic JavaScript code and puts it right in front of your face, you know, 5 lines at a time, and says, this is how object capabilities work. So if you don't feel like really on solid ground, that might be the place to go.
I'll put the link to that in the governance channel on Colab.
Cool.
I don't know that the governance channel is the right place for this discussion.
Yeah,
Jim, what's a better place?
Yeah, what is a better place?
Probably rholang, I would think, or
That's not bad.
I mean, clearly, I'm not sure how it relates to governance. I asked that question, but
Oh yeah, it's definitely tangential to governance. It was just I was talking about governance, and I lamented something about smart contracts being turned off as far as Rev, and then we got onto this tangent. Josh and I did.
yeah, I guess
I mean, in some case, you could call it the whatever it is, the something JS channel, because the Agoric folks use JavaScript. And Mark Miller is on this 15-year. Miller is on this 15-year mission. Go ahead.
You said some JS channel. Would it be the rholang JS channel?
RChain.
I guess so. RChain JS.
We don't have an RChain JS.
Yeah, it's the rholang JS. It's probably what he's referring to.
Okay.
So that's that part rholang, part JavaScript. So that would be a good place to you could go.
Yeah, there should be a lot of discussion about RChain API there.
Right. Okay, so
This is the part where Mojo grabs the leash, and she says, "Time to go home."
Oh, I saw that. Yeah.
Yeah, it's funny when we're going away from the house, she wants to sit and smell everything and look around, and then when I turn around and go home, she grabs the leash.
That's cute.
Which is great for getting exercise.
There you go.
So this would be, watching this video together is close, but have you guys heard of this thing called an upside down classroom?
Sort of broke up there. Upside down. Say that last word.
Yeah, have you learned upside down classroom?
Upside down classroom. No, have not. It's the first time I've heard of it.
So this is what I really want to, so the traditional classroom has zillions of teachers of varying quality lecturing during the day, and the students working through the material on their own at home, right?
Uh-huh.
Homework, right? So an upside down classroom, you take world-class lecturers and you watch their lecture at home, and then you get together with,
Hey, Dan, you're breaking up. Maybe just turn your video off, and I think your sound will come through a little bit more clearly.
It's better?
Not really.
Is this better?
Oh,
Okay,
now-
in a few minutes I'll be in my office.
Yep. Now we can hear you. So,
I'll be in the office.
okay. So,
This discussion that Tomislov had yesterday about setting up ports so we can get into the on-chain rholang.
right.
That was most interesting to me.
So I was watching it and just trying to, everyone was trying to figure out the importance of what it is that they were looking at, and I'm still trying to get my head around it, but it's and I think I have to watch that Arno testing one more time, but yeah, it's another tool in the toolbox that we can use, and I'll have to watch it again to figure out how we can utilize that that tool. He's this tremendous, he's a tool maker for our toolbox. So
Jim, you made a note that you titled his video something to the effect of he's coming up with an idea for a client, but I don't really see it that way that much. He's just actually giving us a way on our own node to talk to the blockchain without having to go through Casper.
Yeah, I mean, in principle, your node's going to be running Casper anyway. But,
Yeah, the contracts are already going to have to go through Casper, so that's not a problem.
but in essence, you're having, your local node has an independent, or can have an independent blockchain. Okay, so it's really so in one sense, it's a partial solution to sharding, in that you have two chains. They don't agree with each other, but they each have a meaning. One being local and one being global. Okay, and the thing that excites Joshi about it is, of course, the idea of rholang for everything, and and that's and from the individual point of view, running a node, it's like they have a client to the blockchain, the global blockchain that runs rholang, and interfaces to the blockchain.
Well, this is, but it's kind of a supercharged client.
Yeah.
I mean, it's a client that can do, it's it's a universal client.
It's like, most distributed applications, the actual contracts are going to be a small part of the code.
Right.
Most of the code is going to be in some other language. Okay, with this setup that
Tomislov.
Tomislov is proposing, you can write almost everything in rholang.
So the one example he talked about was having a contract that would allow him to set up a web server from a rholang program. Did you pick up on that?
Yeah, absolutely. He implemented that. His version of our node supports it. He can listen on a URL and he can send on a URL. So in essence, he can be a web server. And in essence, these and I don't know if he did the WebSocket support yet, but he planned that would be similar to the HTTP support, and it supports channels that go outside of RChain. They're outside of the blockchain.
And do you agree with me that his approach involves moving more of the stack onto the blockchain so that we can reduce the complexity of implementing rholang-based solutions? You see it that way, or is that wishful thinking on my part? In other words, is this going to allow me to do more powerful things within my rholang program? Is this where we're going with this?
I think it does extend rholang. It doesn't necessarily extend the blockchain. So currently we have things like standard out, right? Where the blockchain can touch the world, right?
Right.
Okay. Mm-hmm.
And now the blockchain can touch HTTP.
Yeah, I think Gary's referring to the architecture where essentially you have a standalone node that can talk to, and I guess this is a gRPC interface, or it could be a JSON interface if that's supported, talks to the actual global blockchain.
Yeah, and this is basically the one way to run rholang without showing everybody your knickers. You get privacy this way, right?
Absolutely. That's a good point. I don't think we made.
So yeah, one way to look at this is we're moving more of our dirty laundry under the hood.
Yeah, and it's not necessarily on the blockchain, but it is in the rholang world.
It's sort of like the you can have internal activity in a locality which is not exposed to the outside world, and I see this as a step in decentralizing blockchains when you have worlds within worlds ultimately.
Okay, so I'm still working through trying to understand Tomislov's tool. So it's a tool that allow you to run services locally in the world of RChain that we couldn't necessarily do before, and this was the tool to peer in to query that local environment. Is that sounding
Yeah, well, there's really, there's the web interface,
No,
which is
okay.
one
So
thing, and then there's
web
the
interface.
interface between RChain and an R node instance, which is the other thing that he was talking about. Okay, which he was implementing, as just talking gRPC to between an R node and an independent R node and an R node that's on the blockchain.
Okay, right. So you've got your local R node, and it's communicating with the R node network. Then, and this is the being able to peer in and make the communication between the two.
Right.
Okay.
And I guess part of his justification for that is these extensions that he's proposing, like going out to the web and getting something, for example,
Okay.
tend to not be verifiable. Because when another node goes to verify it, let's say, they're getting the time via a web call. When the node goes to validate it, it's going to get a different answer. So,
Okay. Right.
in order, by doing what he's doing with the architecture, he's saying, okay, I'm going to trust my own node.
Okay.
Be validated. I'm going to query the web, do whatever I have to do to make a decision, and then post the result, maybe a proof of the computation, whatever, to the global RChain network.
Okay.
Okay, and I can do things secret, like I can pass my private key on my own local private node, which I couldn't do to the global network. So I'm not forced to write a complicated client, in order to do this sort of thing.
Okay.
Yeah, it makes rholang an alternative to C or JavaScript or whatever,
Well, that's great. Getting more usefulness out of the rholang languages, being able to have it do more things is that's great.
And this is exactly what we want to do with robots. And
yeah, I realize that.
So as far as incorporating some of what Tomislov has created into robot, do you see a path, or what would be your roadmap for incorporating some of the functionality?
well, after talking to Chris, we'll probably want to move ahead, and it depends on the engagement of people, because right now no one's engaged. But to continue on the path of using the command line through a system call, okay, which would allow us to deploy to work on a local node and then deploy stuff to the testnet or mainnet, sort of on demand.
Okay.
And obviously, we want to replace the command line stuff with the RChain API as soon as it's reasonably ready to do that, whatever. And
Okay.
Chris sort of suggested, for now, focus on the command line, because that's going to have the functionality we need first.
Okay.
But at the same time, I'm hoping to put together enough people who would actually use the RChain API and are willing to learn it and help each other with it, so that we can run a dApp developer session
Right.
actually has people in it that want to use this and want to, learn it, and will participate in work studies, etc., to get their stuff running.
So here's a question I have. So when on one of the calls, Chris Boscolo, he asked, how are people interfacing with our node currently? And no one spoke up and said the RChain API, but the other two options were Ed Eichholt's using the protobuf, and then you said you're using the command line. So how is protobuf different, and what advantages or disadvantages do you have with Ed's means of interacting with the R node?
I have the same problem Ed has with it. It's been really, really difficult.
Okay.
The RChain API is a very thin layer over the gRPC. So it's like gRPC that's slightly friendlier for JavaScript programmers.
Okay.
It gives you some ability to use JSON for data, right?
Right.
So,
but ultimately, do you guys feel that going the API, using the API route, is going to be the preferred method, as opposing the current two alternatives, which are the protobuf and the command line?
Well, everything goes through protobuf, and it's a question of what layer you put on top of that. So even the command line tool goes through protobuf.
Okay.
And it's like, if you're a command line guy, then hey, I want the command line thing, right?
Okay.
If you're a JavaScript guy, you either roll up your sleeves and build your own gRPC client, or you use the one that Josh and I wrote.
Okay.
And then Ed is using Scala.js and a few other and Envoy and a few other technologies to make it a little more palatable.
Okay.
And my hope is that we, provide application developers the GraphQL interface on top of the API, so that it's very easy to use.
So now we bring up GraphQL. So, and I've been trying to get my head around exactly what is GraphQL. Now I'm familiar with loopback. So is loopback and GraphQL, are they equivalent in what they do, or because loopback is kind of like in the middle part of the stack architecture? Is anyone familiar with loopback? Is it possible to make a compare and contrast?
You don't mean the network interface loopback, do you?
Yeah, loopback is, it pulls in all the APIs and kind of is an aggregator or something like that. Well, I'm just not quite clear on what GraphQL is exactly.
That sounds a little bit like GraphQL, but I'm not familiar with it.
Okay, here, let's play a little
as I understand it, loopback is a way of easily creating REST APIs, right?
Okay, so it's a Node.js framework, because when you said loopback, I was thinking of the 127.0.0.1.
Yeah.
So
okay.
Go ahead.
GraphQL is a query language.
Oh, that's okay. That's right. It's a query.
Okay, and it supports queries, mutations, and subscriptions. And
mergers.
Basically is a language that you can put over all your APIs.
Okay.
To make everything available in the same context. So you can, in essence, wire these graphs to point to all your resources wherever they happen to be.
Okay.
So the cool thing about GraphQL is that you can touch it.
Yeah. touch them all.
So look, if you go to developer.github.com v4 Explorer, and if you have a GitHub account, you can sign in so they can do rate limiting or whatever. And the default query here is, what are my last 100 comments, I guess. And you go boom, and wow, okay, that's data that's relevant to my life, right?
Okay.
So that was kind of cool. And so what this particular GraphQL server is connected to all the data in GitHub.
Okay.
But you can take a GraphQL thing and make it and connect it to all the data in the RChain blockchain, or all the data in a SQL database, or whatever.
Got it. Okay.
And this user interface is really nice because it's kind of strongly typed, and it can do autocomplete and all that kind of stuff.
Okay.
So if I go down here and I say B, and it'll can do autocomplete kind of stuff like this.
Okay.
So this is what makes GraphQL really nice is the tooling is really kind of cool. And the based on output is nice. The language itself is like boring. Why do we have to have another one? But whatever.
Yeah.
The other thing about GraphQL is that it allows things like caching and what do you call it? The logical handling of data in the state of becoming. I can't remember the name of what I'm talking about, but with something like RChain, okay, being able to cache all this information is going to make a tremendous impact on the performance of your RChain application. So when a programmer is just using GraphQL to do stuff and doesn't have to worry about caching and all this other stuff, it makes application development really easy.
That might be overselling a little bit there, Jim. I mean, the only two hard problems in computer science are naming and cache invalidation, right?
Yeah, well,
it's true that there's a whole bunch of engineers on the planet working on GraphQL caching.
Yeah.
So you're going to get a lot of help.
Oh, okay. Well, this was enlightening. It just this example here helps me get my head around what exactly GraphQL is.
Right.
Yeah, and it turns the whole world into JSON, regardless of what's on the back end.
Right. If I may, so upside down classroom. Anyway, it's basically where you have the lectures at home and you do the homework together in the classroom.
Oh, okay.
And you use world-class lecturers, and then kind of anybody can be there in the room with you. It's nice to have a really good mentor or whatever, but work with your peers, So we could do a little mix of it with this Mark Miller thing if people are interested, because we could watch the video, and then if anybody has a question, you could stop and I can answer the question.
Yeah, I'm game. I can go for that.
Yeah, some of the work in the Consensus Collab in computational calculus has sort of been like that. They've had a paper to read or something to review, and then they, in the work study, they work out problems.
Okay, yeah, reading groups are kind of like that, I guess, yeah. Okay, so do we want to start with the high-level, really cool stuff that you can build out of the object capabilities, or do we want to learn how get a really solid feel for how object capabilities work?
I think for me, more the higher level before we drill down would be better for me.
Any other opinions? Not hearing any? Okay. So, and I'm going to play it back as like 1.25 or something, because you can hear faster than he can talk.
Okay.
But if you need me to slow it down or whatever, just say so. All right. Now, is this going to, I'll just play it and you tell me, but when I hit play, can you confirm that you can hear it well?
The erights and smart contract.
It's a little quiet.
All right, hang on.
So we've already seen object reference including permission. Permission to invoke an object is a kind of right.
Good. Yeah, now we can hear it.
So when we talk about building erights on top of ocaps, what's the difference in the kind of right that we would build as opposed to the kind of right we already have? We're going to be building the new ones as a pattern on top of the old ones, but the new ones have their own character. So on the left, Alice is just invoking Bob, passing a reference to object Carol. On the right, Alice is paying Bob, over here shown with bars of gold. So the first difference is shared versus exclusive. And this is the remaining line from Alice to Carol on the left. Shows that even after Alice has passed the message to Bob, Alice could have still held on to it. And even if Alice didn't hold on to it, Bob has no way of knowing that, so Bob conservatively assumed that she did hold on to it. Whereas on the right, Bob does not consider himself to have been paid unless he knows that he has exclusive access to the gold, unless he knows that Alice no longer has the gold. There's exercise versus symbolic. Objects are all about the exercise right. You exercise a right when you actually do something with the right, like invoke the object provoking its behavior. Whereas money is just symbolic. It doesn't do anything. It's only valuable because of the expectation that you can trade it to others who will in turn value it. An object, by default, is opaque. When Bob receives the Carol argument, he's just received some object from someone who could send him messages. He doesn't know what the object is. He can provoke its behavior, but he doesn't know what behavior, he doesn't necessarily know what behavior to expect. It requires more patterns for Bob to be able to form such expectation. Whereas on the right, again, Bob doesn't consider himself to be paid unless he knows what it is that he's got, what it is that he's received the exclusive right to.
Did that make sense?
Yeah.
Okay, yeah, I think I can follow.
Right. So if you have some unforgeable name in rholang, you don't know what the heck it is, right? You know you can send messages to it, but that's all you know.
Mm-hmm.
Okay.
Okay.
And then there's specific versus fungible. Each object is unique, whereas the money is just a quantity. Bob doesn't care about one bar of gold versus another, he just cares about the total quantity. Now, it's not that erights represent just the right-hand side, but just the right-hand column. Ocaps represent just the left-hand column, that part's true. But this contrast is showing us a taxonomy with multiple dimensions. And we want a language for talking about electronic rights that covers all the dimensions of variation described by this taxonomy. So this is the age-old mint maker example that's been repeated in the object capability community now for at least 20 years. And the beautiful thing about this example, with regard to the taxonomy you just saw, is that this is all of the code needed to build rights that have all of the attributes we saw in the right-hand column out of object capability that have the attributes in the left-hand column. So this code establishes or demonstrates that object capabilities are a good foundation such that the entire rest of the taxonomy can be easily built by patterns with the object capability foundation.
And okay, so this is that word purse there. That's the same as the Rev purse design, and this is what we currently can't get our hands on. All the purses are sort of locked away behind strings, a big map from strings to purses. So we can't actually write contracts that get access to these things currently.
Thank you.
What's that?
Thank you. I was, I was reading the issue and everything, and that really confused as to what the specific issue was.
Right. This is what gets me all hopping up and down about it.
Yeah. Now I understand what the problem is. Super.
So using that purse example, Alice would have a purse with gold in it. Bob would have his own purse with gold in it. We're going to remove the gold bars from the diagram for the moment to be clear. And Alice would send a buy message to Bob if she wants to, let's say, buy tickets from him. When Bob gets the buy message, at this point, all he knows is he received an alleged payment, but he sends to his main person this deposit method. And when the deposit method acknowledges that the deposit was good, Bob now knows he's been paid without trusting Alice and can release the concert ticket. This fully protects Bob from Alice, but does not protect Alice from Bob. Bob could just pocket Alice's money and then not give a concert ticket in exchange. So what we need, in addition to the taxonomy of rights that include these four dimensions, is we need somehow to build one more element, which is all or nothing exchange of rights. On the left, for object computation, an object message is one way. That's the normal, useful way to do object computation. On the right, smart contracts are generally about the exchange of rights. We need to know that both parties have received the rights that they were looking for, they were expecting in exchange for the rights they were offering, and otherwise that nothing happens. Either both parties are satisfied, or everything is unwound and it's as if the exchange was never tried in the first place. So this is a portion of chainmail, the formal specification language. It's not much of a portion of chainmail. I refer you to the papers you can find linked off agoric.com for more on an earlier version of chainmail. But this portion of chainmail shows the elements of ERTP, the Electronic Rights Transfer Protocol, which basically consists of 3 object interfaces that are related to each other, each of which have a set of methods, define a set of methods.
For just a second here, I'm going to pause here. So did everybody get that he built the purse out of JavaScript, right?
Okay.
And rholang has all the expressivity and encapsulation properties of JavaScript, so we can build purses out of rholang. And all these other things we can build out of rholang if they'll give us the dang purses.
Okay. Dan, one request. Is it possible to slow his speed down just one level?
It is.
Okay.
Then you'll listen to Mark Miller's original cadence.
Okay.
So the purse is the thing that we're doing the deposit to.
That's quite a bit of difference.
So that's the deposit method we see over there.
Yeah, that's too slow.
A particular,
Okay, I see where you're going.
In order to bring about the exclusive transfer, what we need to do is reconstruct the purse example as rights implementing this abstract interface. And the key thing about this abstract interface is that rights across the entire taxonomy, including especially the attributes of exclusivity and the attributes of assay, being able to know what it is you've got, rights across that taxonomy can all be implemented in such a way that they're described by the ERTP protocol. And the ERTP protocol, this set of object interfaces, now enables us to build, and this over here, this is actually the reconstruction of the purse implementation. It's a little bit more code, not a frightening amount of more code, in order to take the same logic and embed it in this very general description of the ERTP. And the result of doing that is we can now create generically parameterizable contracts. Contracts like an escrow exchange contract that handle any right that is presented through the ERTP protocol. So this one contract will deal with rights across that whole taxonomy as long as they're packaged in objects that implement the ERTP protocol.
By the way, I'm not certain what he means by objects that implement the ERTP protocol, but I know that if we studied it for an hour or two, we would get it.
As far as I understand, it's just the interfaces that he previously presented.
Yeah. I'm just sort of like, well, so what if you don't offer one of those interfaces? What happens? That's what I'm not certain about.
It might not work.
Well, yeah, it won't work in some way, but I guess the important part of it is that it doesn't work in the rollback sense, not in the I lose my money sense, right? The other thing is I'll bet you that the rholang behavioral types will just let you have a static type checking error.
Well, this is exciting because what we are learning about Agoric and what we can do with the smart contracts and JavaScripts, we can use that as a model for the future in RChain, in rholang, when that functionality becomes available.
Right, and it's a really, it's like you take their JavaScript code and you convert one line of JavaScript to 1 or 2 or 3 lines of rholang. And it's really, really straightforward to do all the
yeah. Wow, this is thanks for sharing this with us. This is good.
And I suspect you guys can read JavaScript too, right? It's kind of like lots of languages you've seen before.
I have my expertise is in other areas, but I'm sure I can pick it up.
Okay, right. Okay.
And the escrow exchange in particular, for Alice's goal for Bob's concert tickets, is basically the code that you just saw is essentially a two-phase commit among mutually suspicious parties using ERTP to manipulate the underlying assets. So
he went through that all real quick. Is that cool?
Yeah, well, from the video I watched the other day, I understand the principle of what the escrow account and exchange is. So I understand what's going on.
All right. Don't hear anybody else asking to slow down. Okay.
That's the escrow exchange contract, and we'll see this pattern of 5 players a lot. There's the issuer of one of the goods being traded, the issuer of the other good. There's the contract in the middle, and then there are the players. Another example is a covered call option. Let's say that Alice, that Bob offers Alice, Bob, I'm going to hold the ticket in reserve for you. You can buy it anytime within the next week. This is very much like an escrow exchange, except that Bob's tickets are pre-escrowed, and Bob has lost the ability to cancel before the deadline. In the escrow exchange, Alice and Bob could cancel at any time. The covered call is built out of the escrow exchange primarily by the pre-escrowing of the tickets and by taking the cancel ability and putting it in the game clock rather than giving it to Bob. So until the deadline, Bob cannot cancel. Now, the interesting thing about such contracts is this is a contract that unfolds over time. Any contract that unfolds over time, the ability to play the contract while it is in motion, to play the contract prior to the deadline, is itself valuable. For the next week, Alice could spend the money to buy Bob's concert tickets. But let's say that Alice finds out that she has a conflict and she can't actually go to the concert anyway. Well, the contracting framework that we build around the contracts acts as issuer for the right to play that role in the contract as a right described by ERTP. So if Alice wants to sell the option to get the concert tickets to Fred, she can just use the contracting framework around the covered call as an issuer of the right to participate in the contract as the Alice side of the contract. And that becomes an issuer of ERTP described rights into any further contract that can operate on any ERTP described right. So this is fundamentally powerful.
Hold on a second, Dan. That covered call option, that I thought was a tremendous asset to give flexibility, because in the other video they use or tickets, having those tickets, say that relationship is only between Alice and Bob, or for instance, say if you got a ticket to the baseball game, only I can buy it from you. But then I talked to Gary, and then Gary says, hey, I'm interested in going to that game. And then, I find out that, I can't go, but Gary is. Under the normal conditions, Gary couldn't buy that ticket because the relationship is only between the two of us.
Right.
But with the covered option, now I can pass that ability to purchase those tickets to Gary. Now Gary can go and buy those tickets.
Yep.
And that opens up a world of possibilities.
Yep.
That it's that transferability of the privilege to make a purchase.
Exactly. Yeah. Object capabilities let you compose these things in a secure way.
Yeah.
And they let you delegate.
Yes, exactly. That delegation.
From our object-oriented and functional programming paradigm, which is we build abstractions for manipulating objects, and then we package those abstractions as objects, which can thereby be manipulated by other objects. And when we create a generically parameterizable abstraction, like a table, that you can put any object into and take it back out of, then that becomes higher order. It is itself the kind of thing that it can manipulate. It can manipulate objects irrespective of what other objects those are manipulating. So and it's that higher order nature of functions and objects that leads to the composability that has created the richness of the modern software industry and large, rich frameworks and object-oriented libraries and compositions of them. The compositionality of software is built out of that higher order nature. What we see here is a generalization of that from the object rights that are strong on exercise but weak on the other three elements of the taxonomy. We've seen a generalization of that higher order composability across the whole taxonomy. A contract that's generically parameterizable over any right implemented by ERTP, by being a contract in the framework, creates ERTP-described rights for participating in the contract, which means that generically parameterizable contracts can manipulate the kinds of rights they create. And we can now create deep compositions through this duality of rights and contracts. We can create deep compositions that are necessary, we believe, for the richness of contracts that we create to be a rich ecosystem of composition that reflects the richness of the market ecosystems in the real world that are inspiring us to set out on this quest. And now I'll take further questions.
So he does take some interesting questions and stuff, but
in the other video, they had this this graph on the left. This will be interesting to hear him explain it. I didn't get it the first time around. So, machine VATs, JS OCAPs, I'll be interested in to see what he talks about.
Yeah, I mean, when he talks about higher order smart contracts, he's really, in my experience, it's going back to first class objects and polymorphism.
Right, exactly. So the layers underneath here, I don't know if other people want to watch the video. I'm always happy to watch it again because again, I kind of watched. I wasn't there when he wrote each paper or whatever, but it's taken me some number of years to sort of follow all the scribbling bits all over the net that describe all this stuff, and then to have him describe it all in 1 hour is like, oh, that is incredibly cool.
Yeah. Yeah.
The other thing is that he worked on this green stuff and the blue stuff and the orange stuff, since the 90s. And then somebody else built blockchain when he wasn't looking. That's not completely right, but so Mark Miller and Nick Szabo wrote the paper that coined the term smart contract in the early 90s.
Okay. And
nobody knows who Satoshi Nakamoto is, but Nick Szabo is one of the most likely people. It's likely that Nick Szabo and a few other people are Satoshi Nakamoto. So basically, Nick Szabo was down here doing this thing, probably.
Doing the green level?
No, the bottom level, the blockchain level.
Oh, okay, gotcha.
Well, actually, it's this left part of the bottom level. Because he's had VATs and all this kind of stuff running on solo machines, since the 90s.
Okay.
But doing the blockchain thing where you could have this public compute infrastructure, somebody did when he wasn't looking.
Gotcha.
Any other votes for going back and watching some of this earlier stuff?
I'm game.
I'm game for anything.
Okay. That's
all exciting stuff. And
it is. Yeah.
it's like this. I relate it to my recent discovery of Leonard Suskind's QM equals GR. Quantum mechanics equals general relativity.
Oh.
He has.
That's on my to-do list, is to read that kind of stuff.
But it's sort of like he's kind of closed the loop on all these ideas that have been developing over a century. Although he didn't present it all in one video,
right?
He provided the glue that puts it all together.
Yeah, that's cool stuff. All right, so let's go here.
I am Mark Miller of Agoric, telling you about our approach to programming secure smart contracts. As we've seen, people trying to program smart contracts have been making extremely expensive errors, and they're making those extremely expensive errors, including by the real experts who've taken a lot of care trying to program them well. So programming smart contracts securely in the way the industry is doing it now is just too hard and too hazard prone, and the losses are too great. So we have a different way. I'm going to take you up several levels of abstraction. The first one is machines. We're all building on top of computers. Each of these individual planes is a physical machine, but the stacking indicates something else. From our perspective, a blockchain is really just a logical machine. It's a machine that's built out of agreement between a massive number of physical machines, but logically, in terms of programming it, we see it as a machine. The solo machine is actually just a physical machine. It's conventional. And then the quorum machines are where you have moderate replication, give rise to a logical machine. Those would be like permission quorum mechanisms like Hyperledger. So what we want to do is build a level of abstraction across all of these. We want to treat each of these machines, whether they're solo machines, quorums, or chains, as nodes in a cryptographic distributed system. So we're building a cryptographic protocol by which these things can communicate with each other. So the next level of abstraction up is what we call the VAT layer, where each of these green boxes is a VAT, it's a process-like unit. And these VATs speak to each other with cryptographic messages in ways that authenticate who sent the message.
And by the way, when I was messing around with like lockbox designs, I have a strong intuition that what I really want is a VAT.
Okay.
So that's the way I've been thinking about things, but we'll see.
Okay.
What does VAT stand for, or does it?
It doesn't stand for like a vat of stuff, it's of beer or whatever, it's a thing with a bunch of goop in it.
Okay.
And on top of that, we build a system of distributed secure objects, sending messages to each other, where the one object can send a message to another, whether the other object is in the same VAT or a different VAT, or whether the other object is in a VAT on a different machine as well.
Oh, in some ways, a VAT is kind of a trust boundary, by the way.
Okay.
That we have a uniform fabric of objects sending messages to each other. And this is in the object capability paradigm, which is what the ocap stands for. We're actually doing this in an object capability subset of JavaScript. I've been on the committee now, the ECMAScript committee, for 10 years, helping fashion JavaScript into a language that can support this. And then finally, on top of that, we have our actual smart contract layer. By building up to first having a clean layer of secure distributed objects, we now have a basis for building electronic rights and smart contracts in a much simpler and more confident manner, and in a manner that can be made accessible to many more non-expert programmers. And what's particularly interesting, I want to call your attention to the smart contracts and e-rights in a loop over there. E-rights are electronic rights. Smart contracts manipulate rights. But smart contracts, in manipulating rights, themselves create new rights. And the new rights that they create can in turn be manipulated by smart contracts. So this gives rise to a new pattern of contracting that we refer to as higher order contracting, by analogy to the notion of higher order programming in conventional programming languages. Our system comes in 3 protocol layers. VATTP is the protocol that builds the VAT level of abstraction out of the machine level of abstraction. CAPTP, for Capability Transport Protocol, builds the OCAP level of abstraction out of the VAT level of abstraction. And then ERTP, the Electronic Rights Transfer Protocol, builds the rights and contracting level of abstraction out of the object level of abstraction.
I'll just add here that if you have like CAPTP without a blockchain or anything like that, you just have, you know, basically a JavaScript like Node.js will do CAPTP. Or you can just pretend that Node.js is providing you, it does provide you OCAPs. If you just use Jessie inside of Node.js, you can use all the ERTP stuff just with those 2 layers.
Mm.
So as long as you have something that gives you OCAPs, you can play this game.
All right.
The other thing I'm thinking, I don't know how relevant it is, but I think of the higher level programming supporting e-rights as sort of being related to the composability of rholang, in that we can write these abstract methods and use them as building blocks to make programming without making safe programming easier.
Yeah, definitely. And I don't know, I'm not sure. So at some point you can take like JavaScript and send it across the wire like we do between browsers and servers. And so you get mobile code. And rholang does that too. It has this reflective nature where you can take, you know, a process and turn it into a name, and a name and turn it into a process and send them around and stuff. And I don't think that is essential for e-rights, but I think it's another power that can sort of make mind-blowing things yet. I haven't quite figured out where it fits in yet. I think it's more in the living systems kind of stuff. But anyway.
So let's start with the world of objects. And first we're going to work our way down. That'll be the first part of the talk. Then I'll break for questions for a while. Then we'll come back and do the final part of the talk back at the e-rights layer. So the basic step of object-oriented programming is when
So Steve, what have you done any programming?
I go back to basic in high school and Fortran in college.
Okay, so no Java, Smalltalk, any object-oriented languages at all?
That's correct.
Okay. Darn. Well, okay, so basic and Fortran. Yeah, so basically foo here is a function call in basic or Fortran, but it's a function call, and then Bob is the thing that has a few functions you can evoke along with some state.
For Steve's perspective, it might be easier to relate it to the process model.
Oh yeah, so if you're doing rholang, yeah, this is just receiving a message in a rholang contract.
Okay, and I'm getting comfortable with rholang, so
yeah,
making those comparisons are helpful.
Right.
So Bob received the message. So foo foo Carol is sent on the channel Bob.
Right.
And that does something.
Object Alice, it says, for example, bob.foo of Carol, invoking the Bob's foo method with Carol as an argument. So the thin arrows represent object references.
Should we write a teeny bit of rholang that corresponds?
Oh, that would be even better. Yeah.
Boring. My Emacs stuff is all out of whack, so I got to install my Emacs world here real quickly. Okay, now we'll get syntax hiding. Okay, so we're going to have new. Why did I only get one? Oh, well. Let's see. No, I think it's. No, they have to be able to see each other. So actually, it's new Alice. Because Alice has a, yeah, the initial conditions are these: new Bob, new Carol. So Alice can see Bob and Carol, but Bob can't see Carol, and Bob doesn't initially have a pointer to Alice, right?
Okay.
Jim, am I doing this right?
I think so.
Okay. All right, and then
that may not work. I don't know.
so at some point after we do this, let's see, let's move this one up here for a second. Because Alice is going to say, so actually, and oh, and we have to do new Alice in new.
Now, is that syntax correct for Carol?
What the heck is that? Hold on. I don't know what software I've got here doing here. Oh. Somebody remind me how all this stuff works. I forget.
Yeah.
What the heck? Oh gosh, now I'm gonna have to do. I have to map the current working directory into the Docker world.
Oh boy. I don't run Docker for that reason. I always have problems.
Okay, so let's skip Docker. What's the difference between this and this?
RPM is for.
Oh, sorry. Okay, I don't want an RPM.
RPM is for Red Hat or CentOS. Dev is for Debian or Ubuntu.
Okay.
Should be good now. Oops. Is things were still running? Thinks our node's still running?
Address already used. Somebody's doing it. What the heck?
Try, maybe it's running in a Docker container. Try Java. Nothing will make a difference. Whoa, there it is. Kill all Java.
Oh, darn it. I don't want Docker.
Right.
Okay. Now we're getting someplace. Have you guys seen it when I have my dev tools where it'll like put little red squiggles when we're doing it wrong here? I guess I could fire up that other dev tool, but anyway. Line 9. All right. Okay, and then let's actually run Alice. Okay, now Steve, tell me what happened.
Okay, so we've got a channel Alice, and you've got your error logs. Now, there's a few items of syntax I'm not familiar with, but the crux of it, let's see here. So we've got the channels Alice and Carol, and now I don't see a channel for Bob.
Here's where the channel is allocated, and here's where it's kind of, there's a 4 connected to it.
Line 3, makes a new Carol and Bob.
Okay. Oh, okay. So that's okay. So that's the new Carol, new Bob, and as far as syntax, the IN that refers.
That means I get to use the identifiers Carol and Bob for the new unforgeable names inside these squirrely braces, and nowhere else.
Okay. Okay. Okay, that was good. And then, so you're creating a contract Carol, which is empty.
Yeah, we haven't really said anything interesting about Carol.
Okay.
The contract is a read of the channel Carol, and the underscore means read anything sent to the channel.
Oh, okay, that's what I
need.
need. Okay, so the contract is to read. Okay, then we come down to the read of Bob. So you're creating a name foo, and the name X, and so you're sending that log out to Bob foo got. Yeah. And what are we saying? Foo was a function, or
we're saying that that we're listening on the channel Bob for a message that has foo followed by something else.
Okay. When I hear word foo, I think of UFOs.
Yeah, I actually hate it when people use foo. He did this great job of using Bob and Carol, so that you can think of things, and then he goes foo, which is one of these things that doesn't mean anything. So if I make it into a story, the method is called "Let me introduce you to,"
Okay.
Yeah, you see, to understand foobar, you have to go back to Cunningham and Ritchie's original C book.
Yeah, and he doesn't have that context, so let's not go there.
Okay. So.
But you understand. Let me introduce you to, right?
Right. Okay. So. Okay.
Or Bob can now send to, which is the really important thing.
Okay. So bear with, yeah, it's me look through this again and kind of get these relationships.
The other way to do this is to kind of walk through the code in your head in the execution. Let me try that.
Okay.
All right. So this new thing allocates a couple of these unforgeable names. Well, it allocates one unforgeable name and lets us call it Alice.
Okay.
And then it lets us refer to the standard error channel by the name log.
Okay.
All right. And then it does two things in parallel. The first thing it does is a bunch of stuff. It just declares a bunch of stuff that sits there. So now Alice is sitting there listening.
Okay.
All right. And the other thing we do is we send on that channel just something, it doesn't matter what.
Now, when you say you're sending on that channel, I understand being able to send, you need the bang, the exclamation. Right. Well, and okay, down below is where we're sending on that.
Yeah.
Okay.
Okay, so now these two things are happening in parallel, right? This guy is waiting for an input, and this guy's sending. All right, so bang, boom, and nil goes to Alice. Oh, okay, so now this little underscore thing gets filled in by nil. Who cares, right?
Okay.
All right, so now what happens? Now we conjure up two unforgeable names, and we get to call one of them Carol, and we get to call the other one Bob. All right?
Mm-hmm.
And then this bunch of stuff just makes Carol wait. Who cares?
Okay.
In fact, we could delete that, and then our program would do the same thing. We haven't really done anything with Carol. All right. Okay. And now Bob is waiting. And in particular, he's waiting for something of a kind of a pattern. The first thing has to be this string, let me introduce you to. And the second thing can be anything.
Okay. Okay.
That's what Bob is waiting for.
Mm-hmm.
All right. And so he's just waiting. So Carol's waiting and Bob is waiting, and now we get down. Oh, bang! Something's going to happen. All right.
Right.
So now we're going to send. Let me introduce you to Carol, to Bob. All right. And so.
Oh, okay.
All right. So now, there's something waiting for just that sort of thing. Bang! This thing comes to here, and now X gets to be Carol, and it's going to print. It's going to. Then we're going to take Bob can now send to and whatever X was, which is Carol. And we're going to send that to the log channel, and out comes whoosh.
Okay.
So if we could make it slightly easier to kind of understand if we did this. Now that's not an unforgeable name that we can do powerful things with, but it's kind of, if we watch the thing go, Bob can now send to Carol.
Or you could have Carol log what she receives, and
okay,
and have Bob send something to Carol. Right?
Oh crap! We can just.
Now you want to read log, right? Oh no, you're okay. Never mind. Well, he's going to print it.
Okay, so now Alice says, let me introduce you to Carol. And then Bob says, because he just returned, remember when an object receives something, you don't know what the heck it is, right?
Okay,
So
right.
Bob says to X, what is your name? And then Carol receives, what is your name? In some way to speak back to whoever asked her. And she speaks back Carol.
Awesome.
And then Bob is going to, this is the channel he gave to speak back. And so that's going to get printed, we hope. Does that make sense?
Yeah, I get the intuition.
Oops, what did I do? Line 10.
Or a lot. I'm glad you still do that.
Crap. What am I doing wrong here? Oh, I've told it that X is a process, not a name. Okay, so let's turn it the other way.
Not July. Oh, you missed a great session. You'll have to watch the video.
And Steve, we really should just meditate on this until it really makes you can just there's only like one rule in rholang. When an output meets an input, you go. That's the only thing that's going on here.
Mm-hmm.
So if you want, I can rewrite the contract is syntactic sugar for a for. If it's easier, I can only write fors instead of using contract.
Well, that's what I've been exposed to.
Okay, let's do it that way. At least one of them.
Okay.
So instead of that, let's do for. Let's see. And it's a persistent for. Did I get that right, you think, Jim?
That looks right. We're still reading on the channel, Carol, the pattern, what is your name, and something else.
I think we want two different things, not one tuple.
Ah.
I think. I'm less clear on that, but we'll watch it go and we'll see.
Yeah, I think you're right. Yeah, I know I've had difficulty understanding what the difference between an argument list and a tuple is.
Yeah.
It really should be the same thing in my view.
It would be nice if there was no difference, but I don't think anyway, that's not the world we live in. So this contract Bob stuff is just a different way to write a persistent for, a for with this double arrow rocket.
Okay.
So let's see if we got it right. We did.
Okay, so how do you understand this, Steve? Why don't you just go through and describe what you think you understand, and then you can see where the gaps are, if there are any.
Okay. Yeah. Well. Yeah. I can just kind of walk through it. Let's see here. So we've got our channel Alice, and there are our logs that we're going to be sending it to.
We
And
don't send anything.
No, he said we're going to be.
It's going to be.
Putting those names in a context of some code.
Right. Okay. I think he's there.
Right. Yeah, just like you said, all of those. The N is everything is going to be within that that context. So contract Alice. So that could that syntactic sugar for that could have been rewritten as with a for comprehension.
Correct.
As well. Okay, and that would just be an empty. Okay, so we have yeah, even better. Okay. Okay, so we've got our channel Carol and Bob, and those are going to be, as we said earlier, within a set value of unforgeable names. Okay.
Right, but we're not doing that yet.
Right.
We only do that. We only do this if Alice receives some message. Okay, so we're not going to listen on Carol or Bob unless Alice gets a message.
Right. So in some sense, you can just say, "Oh, well, Alice is listening, and then she's going to do something," but we don't care. She's just sitting there. Okay.
And then, so we've had a few things going on in parallel. So we got the top piece, the middle piece. So
well,
1, 2,
there's just two.
3.
Just two.
Well,
there's this whole thing in parallel with that thing.
Okay, because of the braces.
Yeah.
Okay, so everything in the top piece, they're running in parallel within themselves.
Right. So
okay.
None of this is going to happen until
they don't run at all until Carol gets a message. Until Alice
gets a message. Yeah.
Okay. So that was another insight that I needed as far as the overall picture
right.
of what the two halves are. Okay, and that's why. So when we got for comprehension of Alice, which is empty, and then below you've got Alice nil. So it's just sitting there waiting. Okay, so that was a good insight. Okay, and now we're okay. And now, okay, so we've got Carol and Bob. Okay, and then so what is your name? So we've got Carol. So we have persistent. Okay.
She'll answer that question as many times as you want to ask her.
Right. Okay. So what is your name? Carol. Okay. Okay. It keeps coming back. What is your name? My name is Carol. Okay. Then we got contract Bob. So this is another for comprehension.
Mm-hmm.
So we've got the name. Let me introduce you to, and then X. X is some value.
Right. So if he hears "let me introduce you to" and then anything else, he'll jump to action.
Okay. And then we've got then we're sending on channel log.
Well, hold on. Again, these are sitting there waiting. They're not doing anything yet. We got this guy and this guy waiting, and then
Bob did receive that message, so it doesn't do anything
until we get down to here.
Okay, let me digest that.
So when Alice jumps into action, all she does is make 3 things happen in parallel, and the first 2 are just waiting.
It does 2 reads and then 1 write. 2 reads and 1 write.
Yeah.
So if the write matches up with the read, then it can do something else.
Okay, so the key is the process Carol, which kicks it all off.
Well, hold on. Carol is waiting.
Okay.
Bob is waiting.
Mm-hmm.
And then we send to Bob. It's sort of when Alice jumps into action, she's the one that sends to Bob.
Okay, well, if we have Bob bang, isn't Bob the one who's sending?
No, Bob's receiving. This means send on the channel Bob this message.
Oh, it's okay. Send on the channel Bob. Okay, then, okay, the process Carol. Let me introduce you to. Okay.
So Alice says, Bob, let me introduce you to Carol.
Okay, Bob says, let me introduce. Oh, okay, so Bob says, let me introduce you to
No.
Carol.
Alice says to Bob, let me introduce you to Carol.
Alice says to Bob.
Alice received the message, and that caused this write to Bob to happen.
Alice says to Bob,
What
let me introduce you to Carol. Let me put those two in there.
Bob gets the message. Okay, now you could change that back to foo.
Oh, right. So we don't really care what these strings are because we're a computer, right?
Right.
Now this code matches this diagram exactly.
Okay.
What was that before you changed it?
It said, let me introduce you to.
Ah, okay.
This diagram actually comes from social science, where people are being introduced to each other. It's called a Grosvenor diagram. Grosvenor was a social scientist.
We're talking about object capabilities and erights.
Who's just joined?
Mama Chub is here.
Oh, great.
Hey, guys.
Hey. Okay, so we're sending on the channel Bob.
Correct.
The process Carol. So it comes back. What is your name? So okay, and where up at the top is it's listening for that.
Correct.
Okay, that's where what is your name, and that's where we've got. If it okay, that's where the match is. If it comes back, it's Carol. Return it. My name is Carol.
Right.
Okay, that was an insight.
Yeah, we don't want there to be any mystery here. That's completely mechanical at this point, right? You just
okay. So that was the insight that I got to.
So all we've got going on here is things running in parallel, sends, receives, and then the flipping back between ats and stars. That's all of rholang.
Right.
And if a read matches a write, a comma event happens.
Right, and the next step happens that you open up what's inside the for and you do it.
Okay, so that was the insight is the process Carol. Then we got Carol, what is your name? And then return it, my name is Carol. Okay.
Yeah. Oh, and I might have, this might as well be, right? It doesn't, return is not a magic word.
Oh, that was another insight. So return is not is a special keyword with special function. It's just, it could be anything.
Right.
Okay. 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 So we've and then so the middle piece of contract Bob name Foo, how does that fit in?
Okay, so is it comfortable in contract language, or shall I rewrite it as for?
Yeah, if you could do it for now, because that's all I've been seeing.
Yep.
Maybe you should leave the contract in comment or something.
Oh, good idea. Because then he could stare at both of them next to each other. No magic.
Okay.
So we're saying if we send the pattern foo and something else to Bob, then we're going to do the code.
Then we'll do whatever's in here. We'll animate that process.
Okay.
So it just sits there waiting for someone to send the foo. Now Alice did 3 things, right? She said, I'm going to listen for what is your name and the channel, and I'm going to listen for
Foo.
and something else, and then I'm going to send to Bob foo and something else, Carol.
Okay. Okay. Let me. So I'm working on the foo piece. So I understand the Carol. So
Okay. That was the let me introduce you to function called foo.
right. So,
Okay, so at the bottom, we send something to Alice. And when Alice receives anything, she does a receive, 2 receives, and a send. Okay,
Okay.
receipts don't do anything without a send.
Okay.
And then the send is going to go to Bob, which she's listening for Bob, and Bob is going to log. Bob can now send to.
Nope. When you say Alice has 2 receives and a send, I see the one send down below. I see the one receive up at the top. And I'm not quite clear on where the second Alice receive is.
This one right here. You might.
Oh, okay. I'm getting. Okay, I got to get my with the brackets and everything.
Right. There's 3 things in parallel there.
Okay.
She does 2 receives and a send.
Okay. Okay.
Okay, and
Okay, that's the second receive. So now I see the 2 receives. I see the that's there's okay. So now okay. So let me think about that. So now that I understand that there's the 2 receives
and the send.
And the send, right? So the first receive is executed. So my name is
it's not executed. Okay.
Well, right. How did it get executed?
Well, it got executed because we send on the process Carol on Bob, and
Where do we do that?
matched.
Well, hang on. There's these 3 things in parallel, right? So at that step, where are we sending?
We're sending the process Carol back up to it sees the for comprehension of what is your name.
No. We're sending to Bob, right?
I thought we were sending on Bob.
Well, it's to Bob and on Bob means the same thing.
Okay.
Bob is the channel.
Bob is the channel, right?
For foo Carol is the message.
Right.
And this is being sent when Carol receives something. We're sending Bob this.
And she's receiving it because Bob is sending it.
No, Bob is not sending it.
Bob is listening here. We're listening on the channel Bob.
Okay, we're listening on the channel Bob.
What did you do here? You changed it to Alice? Oh, no. Okay. So, given that we have two reads and a write, the reads don't happen without a write. So nothing happens on a read without a write. Okay, the write is to what channel? You have to look at what channel the write is to.
Okay, the write is on the Bob channel.
Correct.
Okay.
So now it's like, what's listening on the Bob channel?
And that's the Alice. Alice is listening.
Well, it's this thing here.
Or that thing there. Okay. Okay, it's listening on the Bob channel.
Right. It's
so
one of the two listens that Alice did is
okay. And we're sending Carol on the Bob channel.
Correct.
Carol becomes X.
And Carol becomes X. Okay. Yeah. Okay, so now that we've got Carol is now X.
Yep.
And then X is turns into a process. Bob can now send to, so is okay, Bob can now send to so that okay. Oh, Bob can now send to Carol.
Right.
Okay. And then we're sending on channel X. What is your name?
That's sending on channel Carol, right?
And X is now right. Okay, X is Carol, so it's sending on channel Carol. What is your name? And then process.
Hey, listening for that. Carol is listening for that.
Yeah, so Carol's listening for that question.
Or we're listening on Carol for that question.
Right.
Okay, we're listening on. Yeah, that one I got to work with. Okay. Oh, okay, we're.
Okay, I think you can meditate on this later.
Yeah.
But I think we kind of okay, but we have a pretty strong intuition that diagram matches this code, right?
Gotcha.
Okay, and we can run this code. And two things happen. It says we can see that Bob can now send to there, and it says my name is Carol.
Gotcha.
All right. Okay. Right. So the code that we wrote, not only Alice sends food to Bob, then Bob goes ahead and sends to Carol, which is the interesting bit. All right. In other words, that's what Bob now has the right to do once he's received that message.
Mm-hmm.
Okay.
And what's shown here is that if object Alice already has a reference to Bob and already has a reference to Carol, then Alice can invoke Bob with that reference. The thing that makes, to get from objects to object capabilities, we only need to impose some restrictions that are very natural restrictions from the point of view of the object program. That these references that carry messages, that those references are the only thing that carries causality. So one object can affect another only by invoking its public interface, and an object can only affect the world outside of itself according to the references that it holds. And the references it holds, as we see here, can also pass. So the result is that references are the only representation of permission. That means that the reference graph from the programming language literature becomes identical to the access graph in the access control literature. And that means that...
And you can treat all that as mumbo jumbo, I don't care.
Okay.
I just know rholang. And you get all that for free.
Cool.
Yeah, a name is in rholang is the same as a reference he's talking about.
Right.
Okay.
Yeah, he's comparing this stuff to, giving this stuff to people with background in programming languages. We don't care. Smart people came up with rholang. They had all that stuff, and they chose rholang such that it has these properties.
Gotcha.
The natural expressivity of object-oriented programming patterns we can now leverage for the expression of rich security patterns including electronic rights and smart contracts. But this dot here creates a problem. This dot is the immediate return control flow, where Alice is invoking Bob right now, does a control transfer to Bob, Bob executes to completion, returns to Alice, and everything that Bob does while it's invoked is part of Alice's transaction.
So this kind of unfortunate doodad here, rholang doesn't have this.
Okay.
So it makes some things a little bit tedious in rholang, but we don't have these hazards. Again, it's like blah, 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 don't care.
Okay.
And because Alice is suspended, Bob could call back into Alice, even though Alice might be juggling a bunch of state, is in a delicate situation, but Bob calling back into Alice in that situation creates reentrancy hazards, such as the Dow bump was an example of that kind of synchronous callback while a caller had various state in the air. So this kind of synchronous interaction is only appropriate locally, only appropriate if Alice and Bob are co-located in the same vat. We introduced this infix bang operator, the eventual send operator, that does an async.
Ta-da!
Yeah. Okay.
Synchronous invocation. Sends the message through to Bob eventually to be delivered to Bob in a separate transaction. And when Alice sends that message off, the message sent immediately returns to Alice a promise for what the result will be. And now.
So in JavaScript, in a lot of programming languages, the return channel is implicit. You don't have to write down the return channel, right?
Okay.
In rholang, we have to write down the return channel.
Gotcha.
Okay. So we got a promise for Carol's name, but only because we wrote it down. So when we asked, we said, okay, Carol, here's a place where you can reply. And so Carol's going to use that to reply. That's why I often call this return, because it's used the same way as the return channel in a lot of programming languages. But it can be a little bit confusing, because then people think that rholang has a magic thing called return. Nope. It returns a word just like you just about X, Y, Z or whatever.
Okay.
Alice and Bob are protected from each other. Alice's transaction completes without being affected at all by Bob's activities in reaction to the message. And likewise, when Bob receives the message, that starts a new transaction. They have nice temporal isolation, keeping them from disrupting each other. So now Bob can be local or remote. Alice doesn't have to care where Bob is. It's the same programming paradigm. I'm sorry, what? It's an object that we refer to as a promise that that is used to designate what the value will be. At some future time, when the value is determined, that object, the promise, actually does designate the value at that time. The cool thing about a promise is the same eventual send can be done on the promise. So if Alice, for example, in this example of Bob here, is itself a promise for the result of a previous operation, then the foo message actually gets queued in the promise, waiting for the promise to get resolved. And once the promise is resolved, it then gets forwarded further to the resolution. So
again, blah, 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 don't care, just rholang, okay?
Mm-hmm.
You do eventual send, you get promises on which you can do further eventual sends. And the promise abstraction we're using here is based on the promises in JavaScript, which are themselves actually based on the promises in my earlier E language, which was designed specifically to have the security properties needed to support smart contracts. Yeah. Great question. The question is, how do you know you got a result back? So there's essentially two fundamental operations you can do with the promise. You can do this eventual send, which just pushes new things in, doesn't ever tell you what you got back. And then there's another operation that there will be an example of later. It's not an example I emphasize, so I'll just tell you about it right now. There's an operation called then. So you say to a promise dot then.
We call it for.
Okay.
You give two callback arguments. One callback is the success callback, and the other is the failure callback.
If you want to do success and failure semantics, you got to build them yourself in rholang.
So if Bob, when he receives this message, if this transaction aborts with an error, then the promise for the result becomes a rejected promise. If the operation returns a value, let's say number 8, then the promise becomes fulfilled with 8. If you do a dot then on a promise with the two callbacks, if it gets fulfilled with 8, then the success callback gets invoked with 8. If it gets rejected with an error, then the failure callback gets called with the error.
So yeah, so no, let's do it. This one's next. This is kind of our return channel here. We can have basically win or lose, you know.
Mm-hmm.
But you can have some sort of if, else, lose. That's one pattern. That's basically the sort of what he's talking about for resolve and reject. It's kind of a detail that does, you know.
You can do if and else in rholang. That's acceptable.
Yes, there is a syntax for that.
Okay.
In general, you can do match and different match arms, but so if is kind of match. But yeah, that is. When I told you earlier that there's no other magic, the one other piece of magic in rholang that's not in row calculus. Well, it's built out of little tinker toys in row calculus, but there's a matcher that makes a lot of things a lot easier. So there's a way to take this if thing and make it into fors and sends and stuff like that, but that would be such a pain in the ass that we don't make people do that.
Mm-hmm.
So I don't know the Java promises. I stopped using Java before they got promises. But what I'm describing is a very direct extension of the JavaScript promises in order to extend them into having the functionality of the full E promises that the JavaScript promises were based on. Okay. So once we can message across machines, once each of these objects might be on a different machine, there are 5 different ways in which this simple diagram can cut between machines. So let's focus in on the most interesting one, which is the one at the bottom. So here, Alice still thinks she has a reference to Bob. Each vat is now divided into 2 portions. Local SES. SES is secure.
Okay, so at this point we have an option on spending our time because the core node engineers built this really cool thing where all this is magic.
Oh, okay.
So when you're writing rholang, you don't know where your code is executing. It's executing everywhere and nowhere, and who cares, right?
Okay.
So if you want to look into the magic of how they think about code moving around and stuff, we can, messages getting from here to there securely, we can do this, or we can skip ahead about 10 minutes.
Well, if it's not applicable to our world of rholang, I'd say skip it.
Well, it's sort of applicable. It's just that, yeah, it's not at the rholang level. Yeah, it's below the rholang level. Yeah, I mean, what the
it's still done within rholang. Okay.
There's something analogous that happens in our node, but like you never looked at all this Scala code that goes and does all this crap underneath, right? You just write rholang code, right?
Right.
So if you want to look at the world that way and just go, okay, magically I get this worldwide computer and I can use it, then we can skip ahead 10 minutes.
Well, the more I understand the depth, it's helpful.
Subset of JavaScript that we created, and then CapTP surrounded. That's the serialization and serialization layer. All of the application the normal application programmer, all of the objects they're normally concerned with are just the ones that live inside the respective SES boxes. All of the rest of this is just the infrastructure that makes it work so that messages can get from one object to another. This CapDP level, in order to do the serialization between these vats, needs 4 tables. It needs a table in each direction between a pair of vats. But these arrows are really way too large to work with, so let's trim down the graphic. But I showed you the arrows in order to have a mnemonic when you look at this graphic.
Actually, this is distinct from the Casper world presents you with one great big virtual machine all over the whole world. Does that make any sense?
Sure.
Okay. This box here actually has 3 different virtual machines or real machines or whatever. So this is much more like what we were talking about earlier with Tomislov having a private node connected to the public node.
Right.
So one of these would be Tomislav's thing on the side, and the other one might be the real worldwide blockchain or something.
And isn't this graphic kind of going back to that very first graphic of the different colored layers?
Yeah, this is the blue layer.
And that right. So, but it's on top of the VAT layer, which is on top of the machine layer.
Yeah.
So the local SES, would that be related to a local machine on the machine layer, or not necessarily?
Not necessarily. You can have a compute environment either just on your desktop or your laptop or whatever, but you can also take all the computers in the world roughly and make them into one thing, right?
Mm-hmm.
And each of these VATs is a machine at either layer, at any layer.
Okay. Okay, but so right now we're just looking at one layer, and that's the VAT layer with the cap.
Right, but these are separate VATs. The whole
separate
rholang is more like one VAT.
Okay. Okay, so rholang is one VAT, and here we're looking at partition VATs.
No, the RChain blockchain network
is one VAT.
Right. Have you ever done so I can do propose and deploy. Have you done that kind of stuff?
I haven't done it myself, but I've been on the calls where people have. Yeah.
And so that you're sticking rholang code into this worldwide computer, right?
Right. Mm-hmm.
Versus when I do eval, I just stick it into a computer on my that I'm sitting in front of.
Mm-hmm.
So that's what I mean by those would be different VATs.
And the other way to think of it is as a VAT being a trusted environment.
Right.
So you could think of it as I'm running a process and you're running a process and Dan's running a process, and each one of these is like a separate VAT. They can't talk to each other unless they share references.
They're also very much like shards, at least I have a vague understanding of shards. I have a very sharp understanding of VATs. But, so there could be a Tampa Bay RChain network,
mm-hmm.
but it doesn't necessarily trust the Chicago one, right?
Okay.
Yeah. So, there's a whole range of things. But whether these are all running, all 3 environments that each of us is running on RChain separately, they're independent. And we trust them, but we wouldn't trust anybody else to come in and monkey with them.
Okay. Mm-hmm.
And now we want to talk safely with each other's environments.
Right, and that's what this is doing.
Okay. Gotcha.
As to what the directionality is.
And this is what I think I might want to build instead of lockers, or
These tables are import-export tables.
Interesting. Yeah. But you still need a locker.
Yeah, maybe.
When
we'll see.
VAT B and VAT C get connected, there will also be import-export tables between that pair.
Well, that's good. I won't worry about.
VAT C
blockers right away.
These two additional tables, the handoff tables.
And, I guess really what I'm concerned about is making a good inbox or mailbox abstraction. I mean,
right. And my intuitions are leaning towards saying that the good inbox thing is really a VAT, but we'll see. I'm not certain about that.
Computation in a blockchain cannot keep secrets. So we had to reformulate a lot of how we're doing things so that all of the access control, all of the distributed security could work without depending on transmitted secrets and without having the object computation at the endpoints internally have to have secrets. So so Bob being entered into the export table that A can use when a message comes in to that B from that A, the fact that it's authenticated as being from that A is a thing that lets that B know that message can address that table. So the index in that table, which is matched between A and B, is how that A talks to that B about Bob. That C can't currently access Bob because Bob is not exported through the export table that C can access. And then the handoff tables have a particularly restrictive rule, which is that C's handoff table from A to B is one where only that A can instruct that C as to what to place into the table, and only that B can instruct that C as to what to take out of that table. That's the A to B table on the left. So when Alice sends that message to Bob, what she's really doing at the object level is sending it to a local proxy for Bob that has to serialize the message. The first step of that serialization is that A sends to that B a give to message. That A is essentially saying to that C, when that B asks you for an index, the Carol A to B is just an index that A made up. When that B asks you for that, give it to Carol. And the message talks about Carol by using the index in the export table that C of the things that C has exported to that.
I'm not going to go slowly through this. If you want, this takes.
Okay, you want if there's another area we should move to, then.
Right, because I mean, there's all kinds of detail, and if you wanted to spend the hours, you could learn this, but it does take hours to learn, right?
Gotcha.
Saying to that B, and that message arrives at that B, and that B proceeds to for me at Carol A what the result of delivers to Bob, and now Bob messages just accumulate through the protocol, and by placing a point to Carol in that table.
The sort of cool thing is you can extend the idea of object capabilities within a trust zone across trust zones if you write some code and you have some cryptography.
Okay.
At the index that we expect.
Actually, I'm not sure this layer uses cryptography.
The index in.
Okay.
Now, in our crypto world, of course, crypto multi-machine world, there's a lot more going on than just serialization and serialization. There's also encryption and decryption and signing and signature verification and a whole routing fabric standing between these machines to get messages from one to the other. And the overall flow is that when Alice sends an object message, it lands in CAP-TP that has to serialize it, delivers it as a serialized block to that TP, then encrypts it, sends it over the network to the other side of that TP that decrypts it into a binary blob that needs to be unserialized into an object message and delivered to Bob. Now,
that wasn't too bad, right?
Yeah, I could follow.
Another important element of making this work is there's this non-deterministic merge, which we can think of as like a traffic merge, where multiple lanes have to come together into one lane. What the overall order is of how the multiple lanes arrive at one lane is non-deterministic. There's multiple possible orders. But that's where fundamental non-deterministic choice has to happen, which is that as the messages come in, they must be delivered into the object world in some specific full order.
So you talk about a lot in the RChain world about this kind of determining the winner of a race, right?
Right.
Right. So that sort of architectural issue shows up in both systems.
And this was the state of our thinking until the alien Satoshi Nakamoto visited our world and gave us new insight that changed everything. So to explain how this whole picture lifts to ride on top of blockchains, I'm first going to take us through the milder step of quorum VATs, of VATs running on quorum machines. So over here, VAT B is a 2 out of 3 quorum. Each layer of VAT B is a separate physical machine. Each of those physical machines can be separately owned, can be in different administrative domains, separately trusted or not trusted, and crucially, in different jurisdictions that are not subject to the whims of any one government. And the definition of VAT B is the enumeration of the 3 participants and the thresholding rule that anything the 2 out of 3 of them agreed on is, by definition, what it is that VAT B did. And likewise, VAT C at the bottom is a 2 out of 2 VAT, so it only proceeds with unanimity. And VAT A, showing it as a 1 out of 1 VAT, is really just the same old degenerate case of just a solo machine. Now, yeah. So the network partition. So if there's a network partition, then the side of the partition in which there are participants, if any, in which there are participants that are able to meet the threshold, on that side of the partition, the VAT can continue to move forward, and other things on that side of the partition can see it. Outside the partition, if you can't receive message from the threshold quorum of participants in the VAT, you cannot see progress. Now, when you get into massive multi-way replication, then you have a lot of the high availability properties that we're used to for blockchains. So at this level, with regard to the individual VATs, nothing we're saying changes the availability characteristics under partition. It's just sort of standard quorum issues with regard to partition. With our fabric going between them, the fact that the messages are individually signed and can be delivered later means that if there is a partition, traffic can just accumulate to be delivered later when the partition heals. So that means that there's not necessarily a logical disruption, and you can still use replication to get higher availability, but subject to all the normal, distributed computing theory constraints on making progress on the partition. Okay. Now, once we have multiple layers, the merge now becomes more interesting because, as I mentioned, the merge is doing a non-deterministic choice. In all other ways, these 3 layers can be proceeding independently, but all 3 layers have to make the same non-deterministic choice to arrive at the same arrival order of messages. So instead of a separate merge per layer, there's a consensus box that cuts through all of the layers, and that's the essential place where all of the layers need to coordinate with each other in order to come up with the overall agreed order. So as the messages arrive individually from other VATs and they arrive individually from different layers, they accumulate in the consensus box until the consensus box can make a joint decision across all these layers about one order. And when it does make that decision, then the consequence of that is emitted simultaneously to all 3 layers. So all 3 layers are like a triple-decker bus of messages.
So Casper is an implementation of this yellow box.
Okay.
So all three layers see exactly the same incoming order of messages. And that's good because the 3 green layers are doing the same kind of job, but they don't need to do it in sync. The 3 blue layers have to be exactly, perfectly in sync, because that's where the validation comes in, that they're reproducing exactly the same computation. Yeah?
Does the 2 out of 3 rule apply in favor of the network partition to consensus as well?
So the consensus, the answer is probably yes. The reason I say probably is I want to say that in defining the VAT, there are two separate policy issues that you can make separately. One is for somebody outside the VAT deciding whether the VAT said something, what threshold they should use, and then there's within the consensus mechanism of the VAT, what consensus rule should be used, and those can use different thresholds. Those don't need to be coupled. But often, they'll be making the same decision across time. Yeah. Okay. So at the when the serialized message is emitted from CapDP and handed to VATDP, it says what earlier messages must be delivered ahead of it. And it actually includes those, it includes the, I'm going to just speak in first approximation, we can come back to it during the QA period. Just, the short answer is, it includes those earlier messages, like the take from includes the give to. Basically, there's a certificate change. So VAT A tried to send the give to VAT C, but then it also included the give to as an opaque payload that got carried so that when the take from went to VAT C, it also carried the give to just in case, so that it could be, so to ensure that it got delivered earlier. But the key thing is that logically every message says what is the tail of the causality chain of messages that must be delivered ahead of that one. So every message has a cumulative hash of the tree of earlier messages. And that way we ensure that a message does not get honored unless all of the earlier messages needed to show that the cumulative hash is correct. Until you see that cumulative hash validate, you don't honor the message.
Is that the feature they're adding to RChain?
They meaning who?
That was announced, I guess, this week, or?
I don't know how that relates to RChain. So yeah, you'd be ahead of me there. I'm not real, I haven't studied that part real carefully.
Some mechanism to tell if a block's been finalized, basically. It's what they're talking about.
Sounds similar.
Which I have wondered how we could do without such a thing.
Okay.
And this sounds like a good way. I mean, we can give a hash that has to be, I guess we have to know what that hash is, but that's one mechanism for determining or checking to see if something's been finalized.
Yeah, I'm not sure.
So at every level of abstraction here, there are adapters, and the adapters each have their own tables. The red adapters might be routing tables and tables network fabric or distributed hash table or whatever. That's the last we're going to mention the routing fabric. We're going to focus in on the green adapters, which are cryptographically how one VAT talks to another. So when object Alice sends that foo message,
is it okay if I skip some of this?
That's fine.
That foo message from A to C, and it sends a message.
Crypto magic, smart people, blah, blah, blah.
Where do I find the link to this talk?
Mechanism as candidate message.
In this 3260 is one of the places there. It's C. Miller at SFBW, and the ERTP stuff starts around an hour and 20 minutes into it. So we watched the ERTP stuff first. Now we're doing the whole thing. Does that make sense, Jim?
Yeah.
I can also, of course, what channel are we living in roughly here, right?
Just be delivered next. Let's say that they're accepted. The post, the recomputation calculates that outgoing message that gets Similarly, it hits the fan-out device. But now, this is...
Okay, hurting my brain. I have to think too hard.
That the VAT level. It's like, hey, we need to equalize. So now that's done copy.
Smart people, I can read other stuff later.
Yeah. Yes, not the internal structure. You need to know what, as a matter of fact, that's the perfect segue for this slide. It's like the perfect question. So the definition of the VAT is explaining how to talk to it. And so when you learn the name of the VAT, you know what devices to build in order to talk to the VAT. So this is a special technique.
Ooh.
Is explaining how to talk to it. And so when you learn the name of the VAT, you know what devices to build in order to talk to the VAT.
So that's exactly the same sort of name when Greg gets all theoretical and weirded out about names and rholang and stuff.
So this is a special case of a very general technique that is sometimes referred to as self-authenticating designators. Things whose name explains to someone holding the name what decision procedure to use to determine if a particular thing is the thing that the name designates. So the most familiar example of this is a cryptographic hash. So when you just have a snapshot of data, if you name the data with the hash of the data, which all of the systems shown in parentheses there do, then anyone knowing that name knows what to do when presented with data that is allegedly the data named by that name, which is a hash. So more generally, the name explains a decision procedure to the entity holding the name as to how it is they should figure out how to authentically deal with what the name designates. So with the VAT ID, the VAT is not data, it's an active computational entity. So the problem we have to solve is somewhat different. There's two subproblems. My name has to explain how to talk to me, and my name has to explain how to listen to me. So when I'm talking, it's cryptographically how to send me messages that I'll recognize, where to deliver them, routing information, etc., and multicast as we've seen if necessary. And then how to listen to me, how to tell if something that I've allegedly said should in fact be treated as something I've actually said. So in the history of this model of computation, it goes back a very long ways. It goes back to the mid-90s, actually. All of those previous systems were using live TLS connections. And a live TLS connection, because of its symmetry, because of its bidirectionality, it solves the whole problem for both sides in one mechanism. But exactly because of its one-for-one live connection nature, it doesn't generalize into the world we're trying to build. So instead, we sign individual messages. Each individual message can be treated as a unit, and now we can accommodate store and forward VATs. As we've seen, a quorum VAT the name of the quorum VAT can list the public keys of the participants, the hosts that are contributing, and can state the threshold for them. Any 2 out of 3 of these enumerated participants are what it means for this VAT to have done something. That's the name of the VAT is the authenticity.
And if you want to play with a quorum VAT, go to GitHub and the code is there. GitHub, Agoric is their organization. I forget which repository it is, but this is all publicly available code right now. It's running.
When they say quorum, there's no association with the JP Morgan blockchain called quorum. Are we talking about something different?
I believe so. We're just talking about the notion of 2 out of 3 or 4 out of 7 or whatever.
So quorum it has its own meaning in this context.
Right.
Okay.
A step toward blockchains. The device you have to construct for talking to a blockchain is essentially a light client, or whatever the light client is, for sending messages into that blockchain. And that's very nice because it's light. Unfortunately, to really listen to a blockchain securely and determine what it said in a definitive manner, the listening device has to be more like a full node, and for blockchains like Ethereum that don't have finality, you have to, in particular, build in front of it finality thresholding, and that's heavy, and I won't be saying anything more about finality thresholding today, but there is an expense in interfacing this to full chains. So that's the end of part one. We've gone through these three layers. Next, we're going to talk about the actual smart contracting layer. Now that we have the foundation, we understand why distributed secure objects can work across the whole system. So if anybody has further questions they'd like to ask here. Yes, please. Okay, yes.
Does everything work with virtual environment, containers, and all that stuff when we talk about machines?
Yeah. So one of the interesting things about a VAT, which I didn't mention, is that the VAT is also the unit of portability, the unit of migration. And when you migrate a VAT, the blue level is the thing that you have to snapshot and migrate. The green level, you have to rebuild a new one around the blue level because that's very dependent on where the VAT is, both what it's being hosted on, as well as from there how it talks to the other things it talks to. But the fact that the blue layer can be snapshotted, moved, and reconstituted is really very, very cool. And because of the store and forward nature of the messages, once it's revived, the old messages that are outstanding to it, assuming that they get routed correctly, the underlying object message within those messages does get delivered, and computation just continues transparently after the migration. Okay, so. Yeah. Yes. The question is, do we have tools that we use to verify security properties of smart contracts? So
this is really, really cool stuff. But again, smart people, you can read it later, hurt your brain right now, okay?
Okay.
The answer yes was premature. This is a long-term activity, but because the collaboration is with all of us together have been working a verification, been trying that of confuse us. So now we're going to focus in on the erights and smart contracting.
We're not going to do the whole thing, but the first little step is really critical.
All right.
So we've already seen OCAPs, object references being permission. Well, permission to invoke an object is a kind of right. So, so when we talk about building erights,
let me just do one thing here in the code we already looked at. So the structure of this is kind of interesting. When a message comes to Alice, she conjures up these two things. And so all of this code, you know, this kind of code can refer to both Bob and Carol, right? So Alice has got can see Bob and can see Carol, right? Mm-hmm. But until Carol comes in here, this code here big mistake. The mistake I've made here as far as security properties is that this code can see Carol, which is wrong.
Okay.
Now wait a minute. Okay, so and then Now Carol's out of scope here. How do I do this? Okay, I have to think about that. How does that work? Oh, it's more like, okay, this hurts my brain. But I think you can see the bug I've made.
Right. Well, how did Carol get?
Yeah, this code right now, the identifier Carol is in scope here, which means that even if we didn't pass Carol on X, we could send on Carol in here. Right? This Carol is in scope here, which is doesn't correspond to Bob. When he wakes up, doesn't have a pointer to Carol, so this code is not quite right. But it's fixable. But I don't want to take the time right now.
Yeah, I mean, if you define Bob and Carol and Alice separately.
Right, and then we pass Bob and Carol to Alice.
Yeah. I mean, somebody has to know somebody.
Right.
To start it, but then they need to pass it. So, but basically, Alice does need to know Bob and Carol.
Yeah, the initial conditions are that Alice knows Bob and Carol, but Bob doesn't know Carol, and Carol doesn't know Bob.
Right.
All right. So I had a little goof there, but we're not going to fix it right now.
So on top of OCAPs, what's the difference in the kind of right that we would build as opposed to the kind of right that we already have? We're going to be building the new ones as a pattern on top of the old ones, but the new ones have their own character. So on the left, Alice is just invoking Bob, passing a reference to object Carol. On the right, Alice is paying Bob, over here shown with bars of gold. So the first difference is shared versus exclusive.
Okay, we've seen this.
Hold on to it. He has object.
I'm going to skip ahead just a little bit.
Okay.
Again, there's true variation.
But last time when we got here, we didn't stare at this closely. So I'm going to see if it's cost effective to do this business of translating this one line at a time to rholang. Oh, that was a mistake. All right, this is a new file. Okay, new bank in can I write contract?
Yeah, that's fine.
All right. New amp in. Now weak map. I'm not sure how to do that yet. But then I write contract mint balance, and I think that's going to be more convenient to treat that as a process. New purse. Contract purse get balance. they're going to make better syntax for this, but it's boring, but this is when rholang is a little bit more boring than JavaScript. So we're going to send to the mint 0, and we're going to receive it back on mch or something. And we're going to do 4m. Oh no, let's see. What are we doing here? We're making a purse. So make purse, we had to turn it into more than one line of code. That's because we did a function call, an immediate function call. And remember, rholang doesn't have immediate function calls. So we had to give a name for the return channel and blah, 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 okay? They're actually going to do syntactic sugar for that. They're working on it.
rholang 1.1.
Yeah. Okay, so that was a little bit boring and tedious, and we were not going to unpack that. But you're familiar with function calls from Fortran and BASIC.
Okay, yeah.
Okay.
You want to make that a contract or?
Which?
The function first.
Oh. We're going to cheat and suppose we have this new syntax maybe. Oh, and you have to, and I'm writing these in parallel, but you actually have to do them one before the other, so we'd have to have some for things to constrain the sequence. And then balance plus equals amount. It's something like this. I mean, we're sort of sending except immediately, and that's where that weird, you know, it'd be nice to have that real syntax so we can avoid this whole pattern here, but let's go just sort of cheat. What did I do wrong there? Oh. Okay, I cheated a small amount, but you watched me take a bunch of JavaScript and convert it to rholang, roughly.
Okay.
And actually, the exact translation is in the core code. It's actually a few versions back because they're not doing it exactly this way anymore. But rolling, the R node had pretty much an exact analogy. Yeah, we used a sealer unsealer instead of weak map, and we had trouble with that. And so they were not confident about the code, and so they backed out of doing it that way. But anyway.
Could you copy and paste this into the rholang channel of Colab?
Yeah, I'm going to do it a slightly different way. I'm going to ask GitHub to give me Scala syntax highlighting.
How do you do that?
I put .scala on the end.
Really? Just on the last line, .scala?
No, right here in the file name when I made a gist.
Ah.
I cheated. The same way I told Emacs to go into Scala mode. So which channel?
Rholang Colab.
Oh, okay. That's in the Rholang JS channel.
Oh, it's up to from JS.
So it would take me about a half an hour to finish this exercise. But you can see that it's not quite one for one because sometimes you have to expand a function call into a longer thing. But they're going to give a syntactic sugar, so it actually will be one for one before too long. And the main point here is no magic up my sleeves, sends, receives, parallel. You know, that's all there is to it. There is some subtlety into why this is secure and stuff that would be a good subject for another day.
Sweet.
But let's take that on faith for now and see if we have an energy to keep going. I have too many windows open. No, I can't get to that one. Right, here we go. So to describe this, when you call the function bank, bank can also be called make mint. If you're looking in the Rholang in the core code, you'll see make mint. And so it gives you back this mint, and a mint has, right, a mint is a function where you give it a balance and it creates that number of things. So what you do is the way you use this a little bit, I'm going to cheat again, but you say gold equals make mint. Let me change this to make mint.
So who was it that said famously that Ethereum contracts are not smart and are not contracts?
I don't know.
But, you know, I mean, if this is, you know, goes back to the definition of what a smart contract is, it seems to me that generally Ethereum contracts are certainly not necessarily that.
Okay, so the way you make this is the mint contract creates a token. And so if you want to, he talks about gold, right? So what we do is we say make mint, and then we say how many gold bars we want, and then the result is Fort Knox. It's all the gold.
Okay.
So if you have that Fort Knox thing, you have all the gold.
Right, right.
Okay. And then he also talks about like tickets, right? So you say like box office equals make Mint.
Mm.
How many tickets can we sell to this concert? 400, say. All right.
Okay. Sure.
You see how we just make new tokens?
Okay, that's helpful.
Right. So in the RChain world, the core code makes rev purses, but we can just use the mint contract and make our own tokens in all day long.
Okay. Hmm.
And no magic. Like if you want to make a new token in Ethereum, well, I guess they just did those out of Ethereum smart contracts. But in Ethereum, gas is Ether is not an ERC20 token, right?
Right. So this meant that these would be tokens that are created specifically for the purpose of that smart contract outside of using a rev or a rock.
Right.
The age-old mint maker example that's been repeated in the object capability community now for at least 20 years. And
there is a 10-page explanation of this thing. If you're interested, I can. That's actually. This is the 10-page explanation. There's a PDF that's about, I don't know, I think of it as 10 pages, and it's, it's 8 web pages or something.
Okay.
This is, and this does make mint, and I think it does covered call and escrow agent. I'm not sure. And that was in 2000. So this is the one that sort of got me into the thing. Anyway, where were we?
Is Mark Milner, is he the author of that capability-based financial instruments?
Yep.
Oh, there it is. Yeah. Mark Miller.
Mark Miller, Chip Morningstar, and Bill Franz. Yep. Oh, I think I have this thing open in 2 different windows. Because this is not where we were. Neither is that. That one's still relevant. Let's get rid of that. Is this where we were?
I don't think we got quite that far.
Yeah, there was.
Here we go.
Yeah, that looks familiar.
the beautiful thing about this example with regard to the taxonomy you just saw is that this is all of the code needed to build rights that have all of the attributes we saw in the right-hand column out of object capability that have the attributes in the left-hand column. So this code establishes or demonstrates that object capabilities are a good foundation such that the entire rest of the taxonomy can be easily built by patterns with the object capability foundation.
Okay. I think I'm going to stop there, but that maybe explains why I'm so depressed that we don't get direct access to rev purses.
Okay. Well, this was all very enlightening. Once we get there, being able to leverage all this information on contract smart object capabilities will be great.
Yeah.
Yep. Thank you so much, Dan. This is really wonderful stuff.
Yeah, this was a good one, Dan. I'm sure I'll be watching it again and again.
Yeah, I'm glad we got it recorded because I need to kind of get up to speed on my rholang coding. So being able to go back and review Alice and Bob and Carol,
Yeah, right.
That'll be good, helpful.
Yeah, you're getting to the point where you can almost start working on the community contracts at the other work studies.
That's my goal. But yeah, if I get there, I'll be proud of myself.
It's the same stuff.
Yeah, I mean, and, you know, but it's the kind of thing where you learn a little bit, and then you got to repeat that 3 times, and then that's a thing you could just have it in your pocket, and you repeat that 3 times, and you have that in your pocket, and that kind of stuff.
Exactly. It's that repetition and exposure. I mean, there's no shortcuts to any of this.
Right.
I noticed that that file that we created, you called it sfbw.row. Did sfbw have any particular meaning?
San Francisco Blockchain Week. It's
oh, okay. I was wondering about that. Okay.
It's this talk.
Gotcha. Good deal. Hey, thanks, Dan. We appreciate the open classroom session.
You know, this one's kind of a long one here, wasn't it? Well, I guess I started with a walk through the woods. So.
Yeah.
All right. I should go live in the real world for a while.
Thanks, Dan.
You're welcome.
Yeah. Thanks, Dan. Thanks, everybody.
Awesome.